Hello, everyone. This is Mike Ritter from SlantRange coming to you from San Diego. Happy to be here today, and I really appreciate everybody coming in to join. It's 9:45, so I think I'm going to go ahead and get started here. I imagine some people might come in a little bit later, but of course we're recording this, so you can always go back if you come in late and take a look. Today's topic: hybrid edge cloud data architectures for beyond visual line of sight drone scalability in agriculture. Quite a mouthful. And before we go anywhere with this, I think the first thing we can talk about up front is why is this important? Why does it matter to me? So I'm going to provide a little bit of background context on that to kick things off. So if you've been paying attention to drones in agriculture, a few years ago, ag was predicted to be the biggest, fastest growing market segment for commercial drone use. And I think the actual rate of adoption has frustrated a lot of those who thought that simply strapping a GoPro to a drone was going to reinvent global agriculture. And the fact of the matter is that the value proposition in agriculture is far more complex than many had envisioned. And in many cases, the solutions are more technically challenging. Nonetheless, there are segments within agriculture that are adopting aggressively, and the rewards are still there. It's a bigger leap than many had originally thought. Like anything, adoption is driven by two things. One is what's the perceived value of the solution, and two, at what cost can that solution be implemented. On the value side, over the course of this last few years, a lot of steady improvements have been made in the value of information that's being delivered for specific applications. On the cost side, a lot of improvements there as well, particularly DJI systems making drone use a lot more usable, reliable, bringing the costs down. If you were using a drone 5 years ago, you'll know what I mean by that. But we're still fundamentally constrained by this line of sight requirement in most places in the world, which says there has to be one pilot per aircraft, and that aircraft has to be flown within line of sight. So for agriculture, where you're talking about huge areas of land that we want to survey, that's a real constraint on the industry growth and adoption. On the horizon, though, we see beyond visual line of sight regulations being passed. There's a lot of talk about that, and that will fundamentally change this dynamic and radically bring down the cost side of the use of drones, and we believe will just trigger much faster adoption in agriculture. But even if we get the regulations passed, even if we have the drone systems that can operate for 10, 12 hours a day, autonomously, we're faced with a major data problem. That's what the subject of today's discussion is really about. So a little bit of background on SlantRange and myself before we dig in. Again, I'm the CEO and founder of SlantRange. We're based in San Diego. Our team has been working on aerial remote sensing and intelligence systems for over 25 years now. In various capacities, and the bulk of that time was actually spent in the defense and intelligence industry. So the aircraft you see in the bottom left portion of this picture, these are unmanned aerial systems operating with more than 30 hours of endurance, many times 12 time zones away from their pilot, and they have a vast array of sensing and intelligence systems on board. On top of that, they were developed at a time before there was reliable high-speed internet all over the place. So the key point here is that beyond visual line of sight, unmanned aerial systems have been around for decades, and they work reliably in a lot of cases. And what we're talking about here is really implementing the same type of thing at lower cost where they can be used for commercial purposes. So back to the value cost equation. Just to give a little bit of context here, we talk about satellites, manned aircraft, and drone systems. When we look at the value of these different potential options in terms of delivering data for agriculture, really what it boils down to is a comparison on the value side of what the spatial and temporal resolution of measurements are. So the fact of the matter is a customer needs a specific type of measurement done at a specific point in time. If it's the wrong measurement, it's not valuable. If it's measured at the wrong time, it's not valuable. If the data can't be delivered in a timely fashion, it may not be valuable either. Drones really overcome a lot of the challenges that satellites and manned aircraft face. On the spatial resolution side, I'll just say that drones at very low cost can exceed a critical threshold where individual plants can be resolved and measured, and that enables entirely new classes of information that you can't get easily from satellites and manned aircraft. That's we could go for hours on that topic alone, but I'll just mention it in passing here. Temporal resolution, satellites are going to pass when they pass, and there may or may not be cloud cover when they do. Manned aircraft have to be scheduled at least hours, perhaps days in advance. But drone systems can be basically launched at will. So when you combine the spatial resolution with that ability to collect data when you need it, really drives the value capability for drone systems much higher than these other options. And we can debate these as well, but the maximum value that we see in different applications ranges from about $10 per acre on a satellite or manned aircraft basis, and there are applications for drone systems that exceed $1,000 per acre. The problem is on the variable cost side, while manned aircraft and satellites are relatively cheap, drones are still relatively expensive to operate, and that's largely driven by this one human pilot per aircraft within line of sight. But we anticipate the cost of drone operations will come back down by at least a factor of 10 and really transform that value proposition equation, and that's what's gonna change everything. Back to what I was saying about data systems, however, just to orient everybody, if this is kind of a typical ag drone mission here. If you're talking about today's M200, M300 class systems, you might be looking at a 30-minute endurance, doing data collections at 100 meters altitude. If you're looking for a resolution of about 2 centimeters, Ortho Mosaicing or image stitching software requires about 70 to 80% image overlap. You run through all those numbers, and you basically end up with a mission that's going to cover about 20 hectares on the order of about 50 acres and produce about 40 gigabytes of raw data if you're using a 4-band multispectral system. So if you get beyond line of sight regulations passed, and you have an aircraft that actually can span the entire daylight range of operations, and you do nothing else, and you basically use today's data system approach, you have an aircraft with 600 minutes of endurance, and at the end of the day, you're going to have 400 hectares collected, or on the order of about 1,000 acres, and 800 gigabytes of raw data, and you're going to be doing that in a place where you don't have humans involved and no ability to really go pull a thumb drive off, and you've got basically it's not a workable solution. So we need to do something to handle the data volumes that these new systems are going to produce. When we start talking about architecting these data systems, what's important to keep in mind is how is information needed and consumed at different stages or different places in an organization. I want to keep that in mind as I talk through the next couple of slides. But what are we doing today to try to improve this data problem? So here I'm listing three general approaches, and the first one I call just raw power, which is to say that we're going to use the same approach to data collection, the same approach to producing image orthomosaics, and we're just going to re-architect the software and massively parallelize computing operations through a GPU to basically produce that orthomosaic a lot faster. There's implementations out there. They work pretty well. They're really fast. The problems primarily are the hardware costs are still high. You haven't done anything to change the data collection costs, which are a problem, and you're still dealing with high data volumes. The second approach is something called quick tiling, which is let's recognize that producing an orthomosaic is the big hurdle here. You need a huge amount of data redundancy, typically 4 measurements for every spot on the ground to produce an orthomosaic, and that amount of overlap requires a lot of data collection time, a huge amount of data processing. But quick tiling just says, look, we know from GPS where every image was collected. Let's just use that information and place images on the ground to create a map and just skip this entire orthomosaicing process altogether. And the advantages there is that, first of all, you get rid of that entire processing step. You get rid of the data redundancy requirements. But the downside is the map tends to be spatially inaccurate, which isn't good for a lot of applications. And the images I show here on right is an Ortho Mosaic result. On the left is what you get from quick tiling, and you see a lot of weird artifacts in how the maps are generated, and it's not an ideal solution either. So the third class is what we call sparse sampling, which is kind of taking this quick tiling step just another step further and saying, well, we don't need any overlap. We'll just take a handful of images around the field and put them down based on GPS or the navigation solution that's in the metadata, and then we'll interpolate in those spaces in between. That's really efficient for data collection, really efficient for data processing. The big problem is you got these gaps in your data for a field. And for a lot of applications, you can't have gaps, especially a lot of high value applications where you really need comprehensive field coverage. So back to this question I mentioned on just a minute ago, when we think about data systems, maybe we should think about them not from the perspective of how do we apply technology from the supplier's point of view to make the data processing more efficient. But let's take a look at this from the point of view of the information needs of the user, and maybe that can help us inform a data architecture that makes a bit more sense. So generally speaking, and when we talk about enterprise level agricultural management, there's different users and different needs of information spanning from the field to a regional manager to enterprise level management. And as an example, a field manager needs the highest density information. For example, if somebody who's responsible for day-to-day field management is looking to detect or identify a pest type for treatment, they're going to need that data collection and data to be turned around very quickly. And many times they're going to want the full resolution imagery at hand so they can actually put some visual look on the data that's coming back. And once you move to a regional level manager, they're not going to need every single pixel that was collected on every leaf, but maybe they still want to see some of the spatial variability across the field. And what you can do is just take that field and grid it up on maybe 10 meter by 10 meter grids. And then rather than reporting every pixel within that field, just report the statistics within that 10 meter by 10 meter grid. And if you do that, you move from about 2 gigabytes per hectare down to 0.001 megabytes per hectare, which is a radical reduction in data volume. And then once you move to the enterprise level management, you can even further reduce it where maybe at the enterprise level, you don't care about spatial variability within fields and you're just interested in the statistics level for individual fields. But the point here is that full field, high resolution imagery really isn't needed past the field. And this is where we start talking about edge versus cloud computing. And it's something that we've spent close to 7 years working on at SlantRange in terms of how do you manage this data flow so the right information is getting to the right users across the organization. So taking the last slide and now looking at it more in terms of data architecture, what this basically means is a system where every drone basically becomes what we call an edge device, which is a completely self-contained data collection, data processing system for that person in the field that needs that information almost immediately. So this basically means moving all of your data processing on board the aircraft and reducing it to a level of statistics that can then be pushed to the regional management center, what we call an edge node, where there might be a local database of data storage. The edge node might contain more computing horsepower to run some higher level analytics. But the idea here is for example, as in a global operation, you might have tens of thousands of hectares spread across a single country. The regional manager might be responsible for that country and is collecting all the data from all those fields and then ultimately reporting up to global headquarters someplace, which is a full cloud implementation, where you have long-term archival storage of data, where perhaps you're developing new models based on data coming in, and you can be pushing new models back out to those edge devices out there as they're created. But the intent here is that we manage how data is processed and delivered at different stages based on the needs of those users. Achieving this, however, requires quite a bit more than just charts on a slide, and quite a bit of innovation. So to talk a little bit about this, as I mentioned before, one of the first problems is this Ortho Mosaicing process. And if you're going to cover a field at 80% image overlap, you're looking about a minute and 40 seconds per hectare to make a collection, or about 2 gigabytes of raw data. But if you can reduce that overlap to 20%, you can reduce the data collection time to about 25 seconds per hectare, and reduce the raw data volume down to about 125 megabytes. That's a 4 times reduction in the amount of time you spend collecting data, and it's a 16 time reduction in the raw data volume. So this might sound a lot like quick tiling, but the approach that we've developed is actually something, it's a bit of a hybrid approach, where we use a more accurate navigation system within the aircraft to more accurately place images on the ground. But once we place them on the ground, we can use some spatial correlation features to tie these things together. And basically we get kind of a hybrid Ortho Mosaic quick tiling approach, where rather than getting this kind of warped looking map, we can actually get a map that looks like it came from a regular Ortho Mosaic. And this is something we've spent a number of years in development on, but it really does deliver these types of advantages in terms of data collection efficiency, data processing efficiency. Another advantage, and if you've never done this before, I recommend you do it. If you look at a high-resolution Ortho Mosaic of an agricultural field, and this is just a small snippet of one Ortho Mosaic we created, and you really zoom in, what you'll see are, and I've outlined some examples here, some weird artifacts in the imagery that you don't recognize when you zoom out, and that's because this software was really developed to create panoramas for photography purposes. These tools are not developed to do quantitative imaging. And of course, what we care about is the ability to extract small pieces of information from this imagery for statistical purposes. So our fundamental approach here, going back to the prior slide, is traditionally you collect a bunch of images, stitch them together in an Ortho Mosaic, and then run your analysis. We've kind of inverted that order of operations, where we collect the imagery, run the analysis on those individual images to extract statistics, and then we aggregate the statistics. So by doing so, we kind of get rid of this whole Ortho Mosaicing process, but we also get more accurate information because we're running it on the raw imagery. We're not running our analysis on an Ortho Mosaic. And if you've ever wondered why stand counts or things like that are inaccurate many times, it's if you're running it on an Ortho Mosaic that's got these types of artifacts, you run into that problem. The last point here I want to make is another advantage in agricultural imagery is there's some new compression techniques where traditionally compression will treat every pixel essentially the same. And when you do that, you kind of destroy some of that high resolution feature that was the point of your data collection in the first place. And you're kind of reversing a lot of your original intent. With agricultural imagery, not all pixels have the equal amount of value. Pixels that have soil information may be lesser in value than pixels that contain vegetation information. And using that, we can decide which pixels to compress. And we develop basically what we call an asymmetric compression algorithm that does not compress the vegetation pixels, but basically completely compresses other pixels. So this provides basically a great form of compression without really any loss of data signal. So once we implement all these types of things, and this is an ongoing work in process, but ultimately what does this enable for these different users across an organization? At the field level, it's the ability to collect high resolution, high value data in a timely fashion and get the results you need, so that manager who's in the field needs to make a decision right now has access to the information they need. The downside of this particular implementation is that you can't get the three-dimensional data out of that quick process result on the field. But three-dimensional data isn't really required that frequently, and that can be done at a regional center where there might be more computing power. So for the regional manager, they get more scalable tools that they can implement more quickly to really start monitoring the statistics on all their production areas and basically enabling dashboarding tools to monitor production. And then on the enterprise scale, basically you have a scalable GIS-based system to really monitor global production at a much reduced cost over what's available today. So finally, just last slide in conclusion before we spend a few minutes on questions. To sum up, beyond visual line of sight tools, together with improved measurement capabilities, are really going to trigger what we've always wanted, which is a broad scale adoption of these remote sensing techniques in agriculture. What exists today in terms of data architectures is going to constrain things, even if we get the regulations and the aircraft tools in place. And from our point of view, developing these new data architectures that can really scale with the ability of the drone systems comes down to really understanding the information needs across organizations and laying down a data architecture that works accordingly. So we'll take a few questions right now. If anybody has more questions, I love talking on this topic. So if there's some contact information, feel free to get in touch with us. Thank you.
We have a question from Juan. He asks, do you see expansion of the drone use in this industry?
Absolutely. As I mentioned, agriculture is an extraordinarily diverse industry, and its needs are accordingly similarly diverse. We are seeing aggressive adoption within specific segments where some of these constraints that I've just talked to aren't such constraints for their operations, and that tends to be more concentrated, high value land, whether it's in high value specialty production crops, or especially within research and breeding applications where the types of information that you can get from these low altitude drone systems really aren't achievable from alternate methods. So yes, we are seeing adoption in select segments, and what I've been talking through today is that beyond visual line of sight tools are going to really change the economics of data collection that will make it much more valuable to broader production, like big broad area row crops. And it's important to note that aerial data can provide an important component of information, but it's not a complete solution many times by itself, and it needs to be combined with other types of information, agronomic expertise from people in the field.
We have another question from Todd, who asks, is this available for use in forestry mapping?
I certainly know of some people that are using drone systems for forestry mapping in a variety of applications, looking for anything from bacterial infections to doing an inventory of tree counts and tree heights and things like that. We have done a little bit of forestry work at SlantRange, but it has not been a real focus. And largely it's because forestry has very large area coverage requirements, which, given the beyond visual line of sight restrictions currently in place, make it a more difficult use case than others that are out there for us today.
Our next question is from Ramon, who asks, what do you think about multispectral information from agriculture? And what about hyperspectral cameras? Are you aiming to use those?
So multispectral, which if some people aren't familiar with, basically is looking at the spectral signature at different points across the visual and maybe into the infrared portion of the spectrum, which can provide markers of health condition of plants. And it can provide much deeper information than you can get from just a color camera, or certainly more than just a monochrome camera. A lot of people are really excited about what hyperspectral can do, and the difference between multispectral. Multispectral in our context today is maybe 4 to 6 spectral bands, where hyperspectral might be 128 spectral bands. The problem is, to get those greater number of spectral bands, you end up trading off spatial resolution. And I need to emphasize that the spatial information can be just as valuable as the spectral information. And having 128 measurements of spectrum on a pixel that doesn't cover or covers both soil and plant, where you're mixing the signals, it doesn't add any increased value. On top of that, hyperspectral just amplifies the data volume problem. So I see it as potential use in the future, but today, the spatial limitations of hyperspectral imagery basically don't bring the value that you should be getting from it to invest in those types of things.
Our next question is from Simcha, who'd like to learn a little bit more about data compression.
Yeah, so digital imagery has been around for decades, and a lot of compression techniques are out there. And then there's different types of compression techniques for video versus still imagery. But the example I showed, I think, was just JPEG compression, but they typically are treating every pixel the same. And my point here was that not all the pixels have the same value in these types of measurements. Pixels that have vegetation information are very highly valued, and we don't want to compress those because compression basically means some loss of information usually. But other pixels, like soil pixels, might not have much valuable to us at all. So we developed a technique that asymmetrically compresses pixels based on the value of information to the end user, and that's the basic technique that we're talking about here. That is, I think, has a real unique value for agriculture. And I think we're probably we got a couple minutes if there's any more questions, but we're almost out of time. Okay, going once, going twice. I appreciate everybody for tuning in with us today in this remote session. As always, we're happy to be a part of AirWorks, and thank DJI for letting us participate and inviting us here. And everybody, enjoy your day, and thank you. And again, feel free to contact us at SlantRange if you'd like to talk about any of these technologies or ideas in more detail. Thank you.